Welcome back. This is the second lecture in programmable logic controllers. Today we're going to review relays. We're going to review the contactor and motor starters. We're going to look at highway diagrams and terminal boards. Then we're going to move on to the Micro800 and explore the different family members. And we're going to focus on the outputs for types B, V, and W. Types Bravo, Victor, and Whiskey. In the last lecture, we looked at relays. We described a relay as a coil of wire and contacts. We used the dashed line here to signify that the contacts and the coils were mechanically coupled to each other. We described this contact as the normally closed contact and this one as the normally open contact. This particular relay would be called a single pole double throw. And you could look at this as if it was a switch in a railroad track where you will either go that way through the normally closed contacts or you will go that way through the normally open contacts. We looked at different ways of drawing the relay. For example, this is a coil. And this is one set of contacts. Here's another set of contacts. If we stopped there, we would have the single pole double throw relay. We'll add one more set, that is. And now we have a double pole double throw. Well, we could keep doing this. If we add one more, we will have a three-pole double throw. So poles refers to each one of these. You could think of this as one pole, this is two poles, this is three poles, and each pole can have two different positions, just like the railroad track here. We can go that way or we can go that way. So it's a double throw. In the previous video, we explored the motor starter. We described the motor starter as two pieces. We had a three-phase contactor, and then we had an overload block. The overload block would respond to the motor overheating and would cause the entire device to trip, thereby disconnecting the motor and preventing it from the overload condition. We made a distinction between the relay and the contactor. And we said that relays were relatively small with a current that was usually less than about 15 amps, whereas the contactor was much larger. They were typically three-phase devices, and they could control from 5 amps all the way up to many thousands of amps. The contactor itself might have several large contacts. We'll draw this as phase A, phase B, and phase C. That might go off to a motor. The contactor might also have several auxiliary contacts. These will be much smaller contacts off to the side. You might have a normally open and a normally closed contact. This is an example of a contactor, a three-phase contactor. You can see the phases 1, 2, and 3 down here. You see the black wires right there. And this particular device has an auxiliary relay block installed on top of it. So here we have a normally closed, normally open, normally closed, and normally open. Again, main contactor has large three-phase contacts. And then the smaller auxiliary block on top has much smaller contacts. Not to be confused with the overload here. Because remember this is a motor starter. This motor starter allowed full current for the motor to pass through the overload block. Again, that is not what we're doing here. The auxiliary contact are very, very small. There's no way you can put any current, at least nothing substantial, through them. So again, we had main contacts, and we had auxiliary contacts. The auxiliary contacts are much smaller. They could only handle an amp or so, whereas the main contacts may be able to handle 5 to, again, 1,000 amps. Let's put this together and explore a motor starter that has auxiliary contacts. This will take me a while. Okay, we're back. This is the contactor, and this is the overload block. This particular contactor has 3 primary contacts for phases A, B, and C, which ultimately go to the 3-phase motor. It has 2 auxiliary contacts, one normally closed, one normally open. The overload block has these heaters that are hooked back to back, and it also has a contact that's normally closed. And this contact, I'll show you in a minute how it operates to save the motor. Now, I'm going to change this drawing a little bit. Give me a moment. We're starting to add the programmable logic controller. We have the input block, we have the output block. This coil is the coil for the motor starter contactor. And I've shown here in yellow the relationship between those particular contacts in the coil. Now we can take one of the auxiliary contacts. Oops, we showed those in purple, didn't we? So we take an auxiliary contact from the motor starter, and we connect it up here. So this is quite useful. So now when the coil is activated, this contact also closes. So the PLC is aware that the motor starter has or has not engaged. The only thing left to do is to add the overload block's contacts. All we need to do now is to add the motor starter overload block. So that contact would exist right here. It's a normally closed contact, and that contact is thermally, I guess you'd say, is thermally related to the heaters inside the overload block. So if any of these heaters, 1, 2, and 3, heat up, what'll happen is they'll cause this relay, this contact down here to open. When that relay opens, this drops out, which means we lose the main contactor. The motor is then de-energized. And the good news is that the PLC now is aware that that has occurred, and we can add code to detect that and take corrective action. Let's go over that chain of events again. So step 1, we activate the motor starter right here. So this is step 1. Motor starter is activated. That causes the main contacts to close. It also causes the auxiliary contact to close. So again, the PLC is aware that the motor starter has indeed engaged. If there is an overload, so put that in purple. If there is an overload in any of these 3 heaters, that will cause this contact here to open. When that contact opens, it's like everything happens in reverse. We lose this, we lose the primary contacts, we lose the auxiliary contact. Again, the PLC is aware that this has occurred, and it can sound the alarm or put the process into a safe state. The next topic on our list was to talk about the highway diagram. This is a trainer that I've put together for you guys that we'll be working with in the lab. We have 3 relays. We have K1 here, K2, K3. We have some switches down below, some motors, terminal board 1, terminal board 2, and wire duct to keep everything nice and neat. This is a picture of the actual device. Again, relay 1, relay 2, relay 3. There's the 3 switches. Turns out that light switches from the local hardware store are much, much cheaper than actual push buttons. We have terminal board 1 up here, and terminal board 2, and then the 2 motors. I'd like to draw your attention to these screws that are screwed into these terminal blocks. We are using the first 4 on the right for positive and the next 4 as the negative. Our switches are connected here. One relay, K2, that's this guy right here, is connected in here. And when I get around to it, I'll wire this K1 into here. Let's take a closer look at this relay right here. You'll notice there are some designations for the screw terminals. You have an A2 and an A1, for instance. If we look at the relay itself, we see this small legend right here. There's A2, there's A1. Here's 11, which is normally closed, to 12, and normally open contact on 14. So if we go back, we can see that here. Here's 11. And those will connect to either 14 or 12. Now all those wires are routed, right? You can see them here. These wires are routed up to these terminal blocks on this side. So I connect them up here, then you connect them down here. Turns out that relays aren't, well, they're kind of expensive, and if you're constantly screwing on these terminals, loosening and tightening them, they wear out fairly quickly. Whereas if I route them up here to the terminal blocks are very inexpensive, and they're fairly robust. Anyway, the point is that these wires, these relay wires, are brought up to this terminal board. And you need to see what's what. So if you look at it sideways, here's K2, A2. So that means there's a wire run from this point here all the way down here to K2, A2. K2, A1, which is the other side of the coil, is run right here. K2A1 is this white with a blue stripe right there. And then you can see the contacts. Here's K211, which is this point right here. And if we look at the contacts, that's this one. That's the common. And then this one here, let's see, can you see which one that is? That's this one right here. That's 12. That's a normally closed. And then this is 14. That's the normally open contact. Actually, we're on the other side, so really we're talking about 21, 22, and 24. But you get the idea. So here's K1, 11, 14, 12. Oops, sorry, K2, 11, 14, and 12. And K2, 21, 22, and 24. Now, I bring up highway diagrams first because they show you where everything physically is, like a map. You know, it's a representation of what you would see if you were to work in a control panel. The points here, again, that's something you'll need to look at. You could look at the data sheet for this relay. Same for this one up here. Or usually you can look at the relay itself and there will be some small diagram that shows you where pins, you know, for example, pin 11 connects to 12 and 14. It'll show you that. These highway diagrams and the terminal boards are really important when it comes to troubleshooting and building your systems. For example, let's say we have a 24-volt source. We have a ground on this side. And we want to power, so this is our goal, we want to power motor, we'll call it K2. We want to power K2 via switch 2. We want to power K2, this one here, via switch 2, which means we need to route 24 volts through the switch. So there's going to have to be a wire coming from here going to switch 2. There we go, switch 2. From switch 2, we want to go to the coil of K2, that's this here. Then we need a wire going from there all the way back to ground. Here's what that looks like. We start at terminal board 1, pin 1, and we run a wire over to terminal board 1, pin 12. We're running a wire from terminal board 1, pin 1, to terminal board 1, pin 12. So that's switch 2 right here. Now I told you I already ran the wire, so there's going to be a wire running from here all the way down to switch 2. Then there's another wire running all the way back. Again, I've already installed those for you. Right, so we're right here. Here's the wire. It goes down to switch 2 and comes on back here. So now, after we've gone through the switch, we're on terminal board, do you see it? Switch 2, 14. So terminal board 1, 13. Here we are. We go to the switch. We come back. We're now at TB1, 13. We need to connect a wire to TB1-24. We go to the coil of the relay. So this was switch 2. This was K2. Come back. We're now at TB1-25. And finally, we need to go to ground, where we're at TB1-5. Terminal board 124 is K2A2, which means that's this point right here on this relay. Terminal board 125 is right here. That's K2A1. That's this one. We are now on the white wire I mentioned before. And you'll need to connect a white wire from here all the way back to terminal board 1, pin 5. Let's do another one. What would it take to activate motor 2 via K2 normally open contact? Well, same thing as before. We need to start out at the positive 24. We'll run a wire to TB1-26. There, we'll find K2 normally open contact. We come back on terminal board 1-27. Now we need to go to the motor, and that's on terminal board 2-7. Here's the motor. A return on TB2-8. Finally, all the way back to TB1-6. So we started here on TB1 pin 2, which is, we just grabbed the 24 volts here. We went to TB1-26, which is this one right here. So that means we're down here on this relay. We return on TB1-27, so that's K2-14, that's this pin here. From there we go to terminal board 2, pin 7, go to the motor, come on back on terminal board 2-8, and then we need a white wire running through the wire duct all the way back to TB1-6. I think I already mentioned this, but you'll need to pull up the data sheets for the relays, and they will tell you what the pinouts are. A2 and A1 are the coils, and then there were normally open and normally closed. I believe it was 11, 14, and 12. And there was another set here, like so, as 21, 24, and 22. Highway diagrams, terminal boards, relays, something to look forward to in the next lab. At this point, we're going to shift gears and we're going to look at the Micro800 family of PLCs, and we're going to look at the input and output connections of those devices. This diagram shows all of the family members that are part of the Micro800 family. We have the smallest, which is the Micro810. Then we have the 820, 830, 850, and 870. Here we're talking about difference in performance and the difference in memory and I/O capability. Devices in green have Ethernet connections. So the 820, 850, and 870, you can just make out the Ethernet connection right there on the 870. Some of these are expandable via plug-in modules. For example, this one can take 2 plug-in modules. This one can take 3. I believe there's some larger ones down here. Yeah, there we go. 1, 2, 3, 4, 5. 5 plug-in modules. And that is to a certain extent defined here. There we go. Plug-in modules up to 5, up to 2. All right. There's another one in blue. This talks about expansion modules. So rather than building on top of the PLC, you can build off to the side. You can have quite a few expansion modules like so. From our previous meeting, you remember the discussion about points? There we said that the points of a PLC is the sum of the number of inputs and the number of outputs. In the lab, we had a Micro800 that had 24 points, which means that it had 10 inputs. Correction, it had 14 inputs and 10 outputs. One quick way to verify that was to look at the LEDs. So there were 14 LEDs for the input and 10 LEDs for the output. We should mention that the smaller PLC has a human-machine interface built into it. You've got push buttons and an LED display. The Micro820 also has a LCD panel right here. Again, more push buttons and a display so you can see what's going on inside. Human-machine interfaces are also available for the larger PLCs. That would be the panel view lineup, and we'll talk about that many lectures from now. Let's take a brief look at the selection guide. This shows you all of the Micro800 family members and accessories, such as the plug-in modules and the LCD displays, power supplies, and expansion modules. What I really want to draw your attention to is on page 9, I believe. There we go. This chart right here is the model number on each PLC, and it's pretty important to us. This 2080, that's the bulletin number. You could consider that simply Micro800. Here's the base family members. So, for example, there's LC30 is for Micro830. The number of I/O, that's the number of points. In the lab, we used one that had 24. Input type, the one we used in the lab had 24 volts. Output type is 24 volts source, and the power supply that it required was 24 volts. We're going to spend the rest of our time focusing on the output type. We have the type Bravo with a 24 volt source. We have the type Victor with a 24 volt sink, and we have the type Whiskey, which is a relay output. We said that the PLC was an industrial computer. It's designed with a hardened shell around some sensitive logic so that that PLC can live in a harsh industrial environment. Inside the PLC, we've got some low voltage, fairly sensitive logic. We have the core, which is this cold fire microcontroller here. We also have a Spartan field programmable gate array. Then we've got some memory chips and a bunch of other supporting circuitry. It doesn't take much to destroy this stuff. Collectively, we're going to call this the sensitive logic of the PLC. In the lower section of the PLC, we have the output and power supply connections. This connector right here connects the robust circuitry down here for the input and output connectors to the sensitive logic that's in the upper assembly. To understand what's going on, it's useful if we look at the output card for one of the older devices. So this is the output module for a SLC 500. And here's what we have. We have this sensitive logic down here, which goes to the motherboard via this connector. We have the output terminals here. In the middle, we have the various transistors and diode clamps. And what I'd like to bring your attention to is this device right here. You see there's a whole row of them. These are called photocouplers. What they allow you to do is to isolate one side from the other. They isolate this side, which lives in the mean world, from this side here, which is where the sensitive logic is. You can imagine if we had a static electricity hit out here, it would come in and it might destroy this transistor, but it's not going to jump this bridge because it's an optical bridge, right? There is no direct electrical connection between these two. So again, what happened, you get a static charge. It might take out the transistor or one of these diodes. It might even take out the photocoupler, but chances are it won't bridge and it won't come here and destroy the sensitive logic, which means that while you may lose one I/O connection, you won't lose all of them, and you won't lose the microprocessor. Back to the Micro 800, those functions are built in. They're just a little more difficult to see. For example, these are the optocouplers right here. There's another one right there. So the photocoupler looks like this. We have a light emitting diode and a phototransistor in a small package. So again, this is the light emitting diode. This is the phototransistor. And this is the barrier. So something bad can happen out here in the mean world, but it will not pass this barrier. In fact, this barrier can withstand a kilovolt or more. Let me show you how the photocoupler is used inside the PLC for the input connections. Give me a moment here. All right, so here we have the external world and we have internal to the PLC. The boundary is the terminals. So here we have input 1, and here is the common terminal. So if you were to look at the PLC, remember we have the input block and we have the output block. We are focused right here on this input block. External to the PLC, we see a 24-volt source that's going through a switch to one of the I/O, through some resistors, and then returning on the common side. In order to get this LED to light, we have to have a complete circuit. For example, if you were to break the common connection, there's no circuit, there's no LED. The LED, once it's lit, goes through this isolation boundary. Again, this is all inside the PLC, and activates this phototransistor. Again, we have things that are external to the PLC. We have things that are internal. We have a requirement that we have to have a complete circuit all the way from the I/O terminal through the LED back to common. And then the PLC takes care of everything else on the right side of the photodiode. That isolation boundary is good for about 1,000 volts. If something goes wrong out here, for example, if you have a static electricity that hits this terminal, it might destroy the resistor here, it might destroy that resistor, it might destroy that LED, but chances are it's not going to bridge this gap and it won't destroy the sensitive logic on the other side. Let's redraw the circuit to make sure we understand. From outside of the PLC, we have 24 volts going to a bus. We have the PLC I/O block. We have a common input 0, 1, input, correction, that's not input 0, 1, that's input 0, 0, input 0, 1, and input 0, 2. We need to connect up to a return. We'll call that ground in this particular case. We can install a switch to input 0. Let's put a push button. There we go. And let's put a normally closed push button here to input 2. Again, this whole thing is the PLC input block. We call this a switch. We call this a normally open push button, and we call this one a normally closed push button. So you could see if we were to move this button in that direction, we would make contact with those. And if we were to push this button in that direction, you would see the contact will be broken. One last time, don't forget this common connection going to ground. If you forget that, then none of these will be operational. And the reason they won't be operational is because inside, that common is necessary in order to light the LED. That takes care of the input block. Let's look at the output block. We'll look at the output for a type Bravo PLC, and that would be a source, or a PLC that has transistorized sourcing outputs. Give me a moment, I'll draw you a picture. This is what a Type B output looks like on the Micro800. Once again, we have this isolation boundary between the sensitive logic and the dangers of the outside world. We have a high side driver, which is a commercial off-the-shelf part that you can purchase specifically for driving loads such as this. This particular one has a limit of 1 amp. To power this device, we need 24 volts from an external source and ground, and those are provided by the plus CM connection and the negative CM connection. The output is shown right here as output 01, and that is used to light this green indicator lamp. Now, there's a couple things to notice. First, this high side driver has some control built into it. It has an overcurrent limit, it has an overtemperature limit, and it does have some degree to clamp inductive loads. Some other things to notice is that everything on this side of the sensitive logic is powered through the external connections, right? This entire high side driver is dependent on these connections here for power. If you forget them, for example, if you forget to connect up the 24 volts to the CM positive terminal, you will not be able to drive anything at all. Let's redraw this from a different perspective. Again, this is for a Type B. Here we have the output block for the PLC. We have a plus CM. We have an output 00, an output 01, and the negative CM connection. We must connect 24 volts here, and we've got to get a ground, a return, whatever you want to call it, down here. Those connections are necessary to power this high side driver. From there, you can connect up your various loads, maybe a red panel lamp, and we'll put a relay here as well. We'll put a diode here as a surge suppression device. That's a type 1N4004 to protect against the inductive kick of the coil when it turns off. Again, I can't stress this enough. You must have connections both to power and ground, going to CM plus and CM minus, or neither of these output terminals will function. And that is because you must provide power to the high side driver. I mentioned inductive kick. Let's take a quick look at that. So we have plus 24 volts. We have a switch. We have an inductor. going to ground. If you close the switch, there will be a certain current that is established in that inductor. Okay, fair enough. When we open the switch, at the moment we open the switch, there will still be that current flowing in the inductor. And that inductor will force the current to continue by increasing the voltage. In fact, it'll increase the voltage so much that you'll establish an arc right here between these contacts until all of the energy that's built up in this coil has dissipated. And that's not ideal. It's not typically going to hurt a switch, but we're not dealing with switches, are we? We are dealing with transistor outputs. Again, there's that high side driver. That's what's actually in this position. It's not a mechanical switch, it's a semiconductor, and that can be easily damaged by this high voltage. So what we do is we install that diode in this position. So we have the diode so that it points towards the plus 24 volt supply. Now, instead of causing the arc here at the switch openings, the current will flow in a loop like this, where that diode catches the high voltage spike, again, completing the current loop. So instead of having thousands of volts, you now end up with one diode drop, which is somewhere around 0.6 volts instead. I learned this one the hard way. I once built a device that had a relay that would toggle on and off, and I was showing it to my boss, and it went click, 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 and then never turned off. Because what happened is that high voltage spike, it went here, and again, it was going into that transistor, and essentially it shorted it out. So that relay was forever energized. I had destroyed the drive transistor. So don't do that. Use those surge suppressors, and all will be well. So that was a type B, type Bravo. Let's talk about the type Victor. Okay, this is for PLCs with a type V output. Give me a moment, I'll show you what that looks like. In this example, we have a low side driver. And you'll notice that the connections to our load, for example, this on output 01, is connected to plus 24. Whereas before, it was connected to ground. So this, the type B, is sourcing, whereas the type V is sinking. Right, so it's taking the 24 volts, going through the load, and the PLC provides a sink or a connection to ground is another way of saying that. Let's go ahead and redraw this to make sure we understand. This is a type V. Once again, plus CM, output 0, 0, output 0, 1, and negative CM. To make this easier, why don't we take this and turn it on its head? The first thing we need to do is connect this up to ground and to 24 volts. So there we are. We have our ground connection going to negative CM and our 24 volts going to plus CM. Our first load can be connected up like this. We'll let that be a red panel lamp. We'll connect that to output 0, 0. Then a coil connected to output 1. Once again, we'll use that surge suppressing diode to catch that inductive kick. You'll notice this diode still points towards the 24 volt supply. Now we've finished. Let's rotate this around and see what we have. So our type V is the sinking type. So each load is connected up to the 24 volts and then the PLC provides a connection back towards common. Again, this coil, the connection will be inside the PLC back to this negative rail right there. That differs from the type Bravo where the internal connections connected each load to 24 volts. All right, one more. And that is the type Whiskey. These are relatively simple. For instance, we have a common 0, and we have an output 0, 0. Internally, there is a relay contact like so. And that's it. It's up to you how to use that particular contact. Right next to it, we have common 1, and we have output 0, 1. Again, it's an internal relay contact. Common 2, output 2, output 3, output 4, and so on and so forth. These are a little different though. So you have shared contacts. So one contact there, another contact there, and another here. So the first two are independent of each other, whereas the ones that follow in that direction do share, or they're grouped together. And it's up to you to decide if you want to have a relay that syncs or a relay connection that sources. If you use a sync, you end up with something that looks like this, where your relay contact is down there. For example, this here might be output 0, 0, and this connection here would be common 0. Your relay source would look like this, where you have the contact and then the load, and the load would be connected to ground. In fact, you could even have it both ways. For example, if you wanted to use common 1 here for 24 volts maybe, and you could use output 0, 1 right there. So it's entirely up to you how you want to use these relays, if you want them to be syncing or sourcing. As we finish up, let's do a quick side-by-side comparison between the relays and the transistor outputs. So relay and transistor outputs. We called these type Whiskey. We called these type Bravo and Victor. Be careful with relays. They have a limited life. We need to be careful with relays because they have a limited life. So mechanically, they're good for maybe 1 million contacts. That's 1 million times of that armature going back and forth before it might mechanically wear out. Electrically, now this depends very much on what kind of load you're driving, but if you're driving a heavy load and it's inductive and you don't have surge suppressors, you can expect that relay to die maybe as few as 10,000 closures, or maybe up to 100,000. Either way, it won't last long, so you have to watch out for that. Do be careful with your relays because the current limit is a function of the power supply. You got to watch out for this, especially when you start leaving the panels. Say there's a short circuit somewhere along the line, so you have a relay output and then there's a short circuit. It could melt the wire, or most likely it'll go back into that PLC and it will melt the traces off the circuit card. The transistors, on the other hand, are overcurrent and overtemperature protected. But you still need to be careful. For example, it's not going to survive if you connect the output of the PLC directly to a 120 volt line. Again, in that case, the magic smoke is going to come out. One last thing, there is a temperature derating that you need to be aware of. So we go from 30 C up to 65 degrees Celsius. And the way the specifications are is that at 30 degrees Celsius, which is still fairly hot, the output might have 1 amp. However, if you get up to 65 C, which is the maximum working temperature for the PLC, you're down to about 300 milliamps. 65 degrees Celsius may seem hot, but not really, especially if that PLC is mounted with other electronics inside a sealed cabinet in an industrial environment. Be mindful of that and do observe these deratings. We'll see you next time.